Okay, so I want to say just a little bit about a symmetric boundary condition before, I don't know how much I'll be able to get to in this video, whether I'll be able to start looking at the homework problem that I mentioned in the previous video or not. But let's say we have our operator, LU, equals minus U double prime, and U satisfies a symmetric boundary condition. The domain is going to be all U's that satisfy a symmetric boundary condition. Okay, then my claim is that in this case, all eigenvalues are real. Okay, and I'm going to do a speed run through this because I want you guys to think about it some on your own. Okay, so let's say we have some function f such that f satisfies the boundary condition, and LF is equal to lambda f. Okay, now what we showed in the previous, you can go back through and show this and show this for yourself in the previous video, is that if I have two functions f and g that satisfies the boundary condition, then this is true. Okay, because the boundary terms cancel when I do integration by parts, and this is what I get. And an operator L that satisfies this equality over a certain domain of functions is called a symmetric operator. And what's also true is it's also true if instead of having a g here, we have a g conjugate here. Okay, and that's the thing that you might have to convince yourself of. But just, we did this before, you can interchange the differentiation in the complex conjugation. Okay, so let's say we have lambda is an eigenvalue. I have lambda times the integral, if I have lambda times ff bar. Okay, so what's happening here? I'm going to use this equality, but with f, like my g is going to be equal to my f. Okay, I can move the lambda on the inside, and if I move the lambda on the inside, it's lambda times f, but then that's just equal to LF. So this is LF times f bar. Okay, but now this is going to be equal to f times lambda f bar, LF bar. But what's going to happen here? This is just going to be equal to lambda f with the bar on top. Now I can move the lambda bar out, and we have lambda bar is equal to ff bar. Okay, now I've got lambda times the integral of ff bar, that's the modulus of f squared over here, is equal to lambda bar times the integral of the modulus of f squared over here. Now I know this cannot be equal to 0, because f times f bar, like I've been saying, is the modulus of f squared. This is a non-negative function. It's not identically equal to 0. If it was, it would mean f is equal to 0. So I got the same thing over here. So I have lambda times a positive number is equal to lambda bar times a positive number. In other words, lambda is equal to lambda bar. And so what this shows us, this is a very general fact. If we have a symmetric operator, that is an operator that satisfies some equality like this, we can state it even more generically using inner products. We have something like this. Okay, this would be a symmetric operator. If an operator is symmetric, then the eigenvalues are going to be real numbers. Okay, so this is something that's going to help us for the homework problem that I'll talk about in the next video, because in that problem we're going to have a symmetric boundary condition, and we know that since it's a symmetric boundary condition, the eigenvalues are going to be real numbers. So I'm just going to not even mention that. I'll mention it. I'll say the real numbers, but I'll refer back to this video. Okay, that's it for this very short video.